This, our country and all its people, could be in danger of nuclear attack in minutes by enemy missiles, in hours by enemy aircraft. Our cities, our farms, our factories. Prime target would be our air bases. With all our aircraft on the ground, our weapons of interception or retaliation not instantly available, we might face another and infinitely more costly Pearl Harbor. To avoid surprise disaster, some of our aircraft must always be in the sky or on the alert, carrying nuclear weapons. These weapons are always unarmed. They will be armed only following a decision by the President of the United States. Only these ready aircraft with nuclear weapons can form our first-line deterrent force in peacetime, our sure striking force in case of attack. We, the American people, understand and accept this necessity for our survival. But we want to know the facts about one question. Do we live in danger of nuclear explosion and radioactive fallout if one of these airplanes should crash, or one of these nuclear weapons accidentally drop? To give you the facts, the United States Air Force presents This bomber carries a nuclear weapon. It is a well-designed, carefully maintained, skillfully flown airplane. But airplanes just like it have crashed and burned. There was no nuclear explosion, no radioactive fallout. These are the facts. The bombardier watches over controls as safe as human ingenuity can make them to prevent accidental bomb release. But nuclear weapons have been dropped inadvertently. There was no nuclear explosion, no radioactive fallout. These are the facts. And specially instrumented aircraft verify these facts in a continuing nuclear safety program that tests our nuclear weapons under controlled conditions that simulate every conceivable hazard. Vital to this nuclear safety program is Air Force Special Weapons Center at Albuquerque, New Mexico. Here, in ultra-modern laboratory buildings, work scientists in and out of uniform. They work with the incredibly complex equations of nuclear physics, which derive from Einstein's famous relationship of mass to energy. These cryptic figures, programmed into lightning-fast computers, are the theoretical base upon which these scientists, together with those of the Atomic Energy Commission, can build nuclear weapon safety. By research, design development, and laboratory test, they ensure weapons not yet built against accidental nuclear explosion. They have been doing this successfully since 1945 in safety conferences with other Defense Department agencies and the Atomic Energy Commission. In 13 years, there have been a few accidents, but not one has resulted in nuclear explosion or radioactive fallout. These are the facts. What keeps our nuclear weapons safe? To understand why there has never been an accidental nuclear explosion, you must first know how these explosions can be produced, the general principles of nuclear explosions.
Any explosion is the result of a very rapid release of a great amount of energy. Conventional explosions result from the rearrangement of whole atoms in some explosive material. For example, in TNT, the rearrangement of whole atoms of hydrogen, carbon, nitrogen, and oxygen produces explosive force. On the other hand, nuclear explosions result from the rearrangement within each atom. This may be a joining together or fusion, as in an H-bomb, or the splitting apart or fission, as in an A-bomb. At present, an H-bomb explosion starts with fission, so the splitting of the nucleus of the atom is the basic principle of nuclear weapons. All matter is composed of one or more of the 100-odd elements. Of these, the atoms of the metals uranium and plutonium can be most readily fissioned to cause nuclear explosion. These elements are mildly radioactive. They emit short-range, low-penetration alpha particles while in their unfissioned state. These alpha particles do not have the harmful effects of the longer range and stronger gamma rays, which are given off by certain elements such as radium or by the products of nuclear fission. The atoms of uranium and plutonium are among the heaviest. Heavy because the nucleus of each atom contains large numbers of the fundamental particles called protons and neutrons. When a free neutron hits this nucleus, it splits into two parts, releasing more neutrons which may go on to split other nuclei. The resulting fission products become highly radioactive, emitting the long-range and dangerous gamma rays. The split nucleus weighs less than the whole one, and this difference in weight is released in the form of energy, nuclear energy. After fission, harmful gamma radiation. Before fission, innocuous alpha radiation. To build up a nuclear energy release, the fissionable material must be of a certain size, shape, or density. Then one of the neutrons escaping from a split atomic nucleus will, in turn, split another, and a chain reaction is set up. The mass is now releasing nuclear energy, but not quickly enough to cause a nuclear explosion. This condition is called critical. If the mass is now suddenly increased, so that more neutrons are trapped each time an atomic nucleus is split, a multiplying chain reaction is maintained. Now the mass is supercritical, causing a nuclear explosion. Density of the fissionable material can be as important as mass in building up a nuclear explosion. The same sphere can be compressed so that the atoms are closer together and neutrons split more atomic nuclei, making the smaller mass critical. If compressed still more, a multiplying chain reaction sets in, causing the mass to become supercritical in a nuclear explosion. Nuclear weapons make use of both of these principles. A gun-type device can increase the mass of fissionable material to a supercritical state instantaneously. One subcritical mass is propelled forcibly into another by an ordinary powder charge. The increased mass becomes supercritical. A multiplying chain reaction builds up until the nuclear explosion. Obviously, if any mechanical device keeps these two subcritical masses apart, the weapon is nuclear safe. Applications of this fact prevent accidental nuclear explosions in gun-type weapons. Another kind of nuclear weapon is the implosion type. It compresses the fissionable material to greater density to make it supercritical. To do this, the sphere is enclosed by a shell of ordinary explosive designed to direct its explosive force inward. This effect is called implosion. The detonators attached to the explosive are connected to a complex firing device which can fire every detonator simultaneously. When all the explosive is detonated simultaneously, the nuclear material is compressed into a supercritical mass, which results in a nuclear explosion. Implosion-type weapons are nuclear safe because only the specially designed firing device can produce the simultaneous detonation of all the ordinary explosive, a deliberate effect possible only by the precise firing mechanism. Should a single detonator be fired accidentally, whether by malfunction, crash impact, or fire, the explosive would not provide the all-around compression necessary for implosion. Instead, it might push the nuclear material out of the shell, break it into small pieces, or even burn it. This unfissioned material emits only alpha particles because no nuclear explosion has taken place. These alpha particles do not penetrate the skin. The simplest precautions can prevent their intake into the body, and the simplest cleanup measures can remove them. So you see, each type of nuclear weapon has its own safeguards against accidental nuclear explosion. These are the facts.
And they are based upon practice as well as theory. Specially instrumented aircraft fly the tests that verify what happens inside a weapon, what accident hazards the nuclear components may have to withstand. Nuclear safety is everybody's business. Although Air Force flies the test missions, scientists and technicians from the Atomic Energy Commission and other services man the test range and evaluate the findings of the elaborate instrumentation. Drop tests measure impact characteristics of various weapon types. They are made without nuclear components so that this precious material is not wasted. They supplement the detonation tests that have been made with the complete nuclear weapons. Impact or shock does not cause nuclear explosion or radioactive fallout. What has exploded is the ordinary explosive, which is an essential part of nuclear weapons. The ordinary explosive in a nuclear weapon can be a hazard, exactly as in a conventional bomb. Depending upon the amount and location of the explosive and the speed and height of the drop, we may experience a variety of ordinary explosions. Large ones, small ones, or none at all from impact of the bomb. Beside the hazard of impact, frequent tests are run on the hazard of fire. To learn what temperatures and pressures would be created inside a weapon by an aircraft fire, various types of bombs are subjected to a flame bath of burning fuel. Because fire would also destroy the precious nuclear material, it is replaced by instruments. Their readings are compared with known characteristics of the fissionable material to assure that temperatures higher than any aircraft fire will not set off a nuclear explosion. The characteristic white flame indicates that the ordinary explosive is burning in the weapon. Sometimes the explosive detonates because of close confinement and intense heat. The effects of such explosions are measured and compared with those in an actual nuclear weapon. Fire and ordinary explosives do not create the conditions necessary for nuclear explosion. These are the facts. And on the vast desert ranges of the Atomic Energy Commission, the facts are verified by safety testing live prototypes of all new weapons before they go into production for our stockpile. The tests are costly in money and manpower, even more costly in the fissionable materials on which our nuclear strength depends. But they do provide insurance against nuclear accidents, which make them a bargain at any price. Some take place deep in the earth. Fantastically complex instruments replace the five senses. They record what happens when some of the explosive that surrounds the nuclear material of a new weapon is deliberately detonated. They record only an ordinary explosive blast. A random detonation has not created the implosion which would compress the nuclear material to a supercritical mass. There was no nuclear explosion, no radioactive fallout. Each new design must be proved nuclear safe, able to withstand accident, fire, or random explosive. Other tests with nuclear weapons are made above ground. These are also designed to test the nuclear safety of new weapon types by intentionally detonating the explosive which surrounds the fissionable material. Sometimes these tests also provide data on the side effects to be expected if the fissionable material is broken up by the explosion. Air samplers and test pads are used to gauge the area, intensity, and duration of these side effects. In this way, they learn not only what does not happen when a charge is deliberately fired, but what does. The explosive does break up the nuclear material and scatter parts of it over a small area. This fissionable material is mildly radioactive. If the explosion or fire should suspend any of this material in dust or smoke, it should not be inhaled or otherwise taken into the body in quantity. That is why the trained monitoring and cleanup crews may wear respirators until air samplers or alpha counters have determined that no injurious concentration exists. The alpha particles emitted do not penetrate skin or clothing, so this material is harmless when on the ground. Only simple cleanup measures are necessary, plus an effort to find and save the valuable material. The findings from all tests set up to measure possible radiological hazard are no external radioactive hazard from material on the ground, slight radioactive hazard from prolonged inhalation of material suspended in a small area near the accident, but none from the short exposures necessary for firefighting, rescue, or cleanup of the small area involved. These are the facts. Facts that have dispelled the fearsome myths about accidents involving nuclear weapons. For anyone near an accident, whether or not the crashed airplane carries a nuclear weapon, here are the safe and simple rules. Stay away from the crash unless you are needed for rescue. Bystanders endanger themselves and hamper others. To be safe, keep at least a quarter of a mile away from any burning airplane. At this distance, you are safe from the flames, which may explode the jet fuel, from detonating explosives, and from flying debris. These are the real dangers in rescue or firefighting, as they have always been. The trained men who bear these responsibilities know how to do their job and get quickly away from all these hazards. After the emergency is over, the area is monitored for radioactive material and, if necessary, cleaned up by specially trained teams. Other specialists care for burned or undetonated pieces of ordinary explosive. Until this is done, access to any crash area is controlled to prevent accidents and speed up the work. The tests you have seen have proved the safety of our nuclear weapons program over and over again. But the grim reality is the payoff. How safe is a nuclear bomber coming in for a crash landing? Not the impact of the crash landing, nor the fire which often follows, not even detonation of the ordinary explosive in the weapon, cause nuclear explosion or radioactive fallout. The safety that was designed in during research, built in during development, proved in the laboratory and on the range, has withstood the ultimate tragic test. These are the facts. They prove that you, the American people, can stay both safe and strong. Safe because the weapons your Air Force must carry have been tested nuclear safe. The possibility of an accidental nuclear explosion is so small as to be practically non-existent. Strong because an Air Force, nuclear armed and combat ready, stands guard against surprise attack. Under this shelter, you and your family may live in peace, free from the fear of nuclear accidents.